Hello. So as promised, let's go through the graph of this function. And we'll just look at all of these points so that we know exactly how to graph it. So the first is to determine the end behavior of the graph. So the end behavior for point 1, we want to look at the leading term. And since this is already written nicely for us as a polynomial, the leading term is just going to be x to the third, which we see has an odd power and a positive coefficient. The coefficient is hiding, it's just the number 1. So we know that whatever our graph looks like, because this is an odd function, or sorry, because this is an odd power, that's the word I'm looking for, we know that it's going to go up in one direction and down in the other, and since this is positive, as x gets really big, our function is going to get really big, and as x gets really negative, we're going to go down. So who knows what our function is doing in the middle, but we know that as we go far to the right, we're going to go up, and as we come to the left, we're going to go down. So let's find the zeros and their multiplicity. So what we want to do is solve when is this function equal to 0. Again here, this is in this case, this is fairly simple because I can factor this. I can factor an x squared out of both terms. I factor an x squared out of the first term, I just left an x, and I factor out of the second term, I'm left with a 3. So this is already very nice. So when I want some numbers multiplied together to get 0, one of those two terms has to be equal to 0. So x is equal to 0, or x minus 3 is equal to 0. So my roots, or the zeros of the function, are when x is equal to 0, or when x is equal to 3, if I add 3 to both sides. How about their multiplicity? So here I have an x squared. The second power here means that 0 is going to be a root of this twice, whereas 3, this means that the multiplicity is going to be exactly 1. So what's important here is that this is an even multiplicity, and this is an odd multiplicity. So the graph at x is equal to 0 is going to come up and touch the x-axis and turn around and run away. Here at x equals 3, because we have an odd multiplicity, the function is going to cross the x-axis. So if I draw our picture again, if I point out 3 and I point out 0, I know that my function is going to come up and just barely touch 0 and turn around, but it's going to cross at 3. And if we remember, our end behavior, we're going to be coming up as we go to the right, and we're going to be coming down as we come to the left. So what we know is that we're going to come up and touch the x-axis there, and we're going to turn around. And then we have to cross 3. So the only way to do that is to come back and do this. So this is what our function will roughly look like. This isn't exact at the moment, this isn't precise. All I've done is I've connected the dots. Again, how have I done this? We've got the end behavior, so we know we have to be coming down to the left, and we have to be going up when we're going to the right. We have to touch 0 but turn around because this has an even multiplicity at this root. And at 3, we're going to cross right through the x-axis because we have an odd multiplicity. So that was finding the zeros, as in the roots and their multiplicity. Next, we need to find the y-intercept. Well, from our graph, the y-intercept should be at 0. But let's check. It's always important to check our work. So the y-intercept is when I plug in 0 into my function to see where it's going to cross this x-axis. Well, our function is just going to be 0 cubed minus 3 times 0 squared. Well, that's 0 minus 0, which is 0. So, very very, very nice. Our y-intercept is directly at 0, which is just checking exactly what we've seen before. The last bit is to use some symmetry before we check the turning points. So let's check the symmetry. We have, I've run out of paper, so I'll just continue on. Remember that if we have an even function, this is when f of x is equal to f of negative x. And when we have an odd function, this is when f of negative x is equal to negative f of x. So all we have to do is plug in negative x into our function, and we see, do we get the original function or do we get negative of the original function? And it could be that we get neither. So let's try this. For our function, we have our input cubed minus 3 times our input squared. So when we cube negative x, we're going to get negative x times negative x times negative x, which is going to be negative x cubed. If we square negative x, the negatives cancel out. And we're going to get positive x squared, and positive x squared times negative 3 will be negative 3. So this is our function f of negative x. But f of x, which we just used, is x cubed minus 3x squared. Those aren't the same. So these guys aren't the same. What about negative f of x? Well, if I just add a negative sign in front of everything, I get negative x cubed. Negative negative 3x, this is going to be positive 3x squared. Are these guys the same? No. So because these two aren't the same, this means that we're not even. And because these two are the same, these are not odd. And if we come back up to what our function supposedly looks like thus far, we can see that this isn't going to have reflectional symmetry about the y-axis. If we flip it over, it's not going to look the same. Also, if we rotate this 180 degrees, it's also not going to look the same. So more or less, this was just checking whether or not these things are true. So this was point 4. And then with point 5, when we look at our function, what's the degree of our function? Our degree of our function is going to be 3. So the number of turning points of our function has to be less than 3. So we should have fewer than 3 turning points. Well, if we come back up here and we look, I have 1, 2 turning points. That's less than 3. Everything checks out. So this is our rough drawing of x cubed minus 3x squared.